So now let me go and draw the Bode plot. Okay, with all this background, let's go and now construct the Bode diagram for this particular second order transfer function. Okay, so how does it look? So let's draw the Bode plot. Let me first draw the magnitude plot. So of course we are going to consider omega on a logarithmic scale, and on the y axis we have the magnitude of g omega in decibels. Okay, so let's say this is the 0 decibel line. Let's say this is let me just redraw this. Okay, so let's say like this is the 0 decibel line. Let's say this is minus 20. Let's say this is minus 40. Okay, so that's what we have. And let's say this is omega n. Let us say this is 10 times omega n. Let us say this is 0.1 times omega n. Okay, because I am considering the natural frequency as a corner frequency. Okay, so let me use the same color code as yesterday for the asymptotes. Let me just scroll up and see what colors I used. So for the low frequency asymptote I use pink and yellow for the high frequency asymptote. Okay, great. So the low frequency asymptote here is going to be the 0 decibel line once again. So this is the pink line as the low frequency asymptote. So the high frequency asymptote is going to have a slope of minus 40 decibels per decade, right? So at omega equals omega n, the high frequency asymptote will be value will be 0. At omega equals 10 times omega n, what should be its value? Minus 40, right? Because in one decade it decreases by minus 40, right? So at omega equals 10 times omega n, we are going to have minus 40. So as a result, the high frequency asymptote is going to be something like this. Okay. So I am just extending it to show it graphically. Okay. So but this is the high frequency asymptote. The slope is minus 40 decibels per decade. Okay. Now the point is the actual curve, okay, depends on the value of zeta. Okay. So please note that the maximum amplitude occurs at omega equals omega n times square root of 1 minus 2 zeta squared. Okay, that's the resonant frequency. So as zeta increases from 0, what do you think will happen to this resonant frequency? Will it become less than, will it go towards the left of omega n, further to the left? Yes, because as zeta increases, you see that 1 minus zeta 2 zeta squared decreases. So as a result, as zeta increases from 0, the further the increase in zeta, the further is the shift of the resonant frequency to the left from the natural frequency. So I am just going to draw a family of curves, so which will essentially tell us how the natural frequency curve looks like. Okay, so this is the actual curve. So let us say low damping ratios, I have this. Okay, ultimately it will go and coincide. As the damping ratio increases, the peak essentially shifts further and further to the left. Okay. Okay, but anyway, after some time, everything goes to the high frequency asymptote, right? So yeah. So I am just drawing a freehand sketch, so please pardon the approximate diagram. Okay. So what happens is that this is how the peak changes, right, as zeta increases. Of course, after zeta greater than 1 by root 2, you see that the maximum value never crosses 0 decibels. Okay, that means that there is no peak as such, right, for zeta greater than 1 by root 2. So that's why the maximum value is 0 decibels, right. So, that is it, the low frequency asymptote is the highest value. Okay. So, that is what happens. Of course, what happens to this magnitude plot for an undamped system? What do you think will happen? You will see that once again low frequency asymptote will be 0 decibels, high frequency asymptote will have a slope of minus 40 decibels per decade, but what will happen at omega equals omega n? You will see that the amplitude will blow off to infinity, right. So, essentially that is what we have, right. So, essentially it is going to be a very high amplitude. So, what do I mean by that? Let us say, like let us say we consider the undamped system, okay, omega n squared divided by s squared plus omega n squared. What is going to be g of j omega? It is going to be 1 divided by 1 minus omega squared by omega n squared, right. So, what is the amplitude? It is the same, right. So, essentially, but anyway, there is no imaginary term, okay. So, you get the same thing in essence, right. So, if I rewrite this, this is going to be 1 minus omega squared by omega n squared, right. Of course, the absolute value, right. So, you need to take the, so you can immediately see that what happens as omega tends to omega n, the amplitude just blows off to infinity, right. So, that is what you have, okay, when you have the what to say, for an undamped system, okay. So, this is just an aside, right, okay, fine, okay. Now, this is the magnitude plot, okay. So, this is the magnitude plot of the second order term that we have been considering. Now, what about the phase? So, please note that the phase is going to be g of j, phase of g of j omega was essentially what, minus tan inverse of 2 zeta omega by omega n divided by 1 minus omega squared by omega n squared. So, one can immediately figure out that this phase goes to 0 degrees as omega tends to 0, this goes to minus 90 degrees as omega equals omega n, okay. This essentially goes to minus 180 degrees as omega tends to infinity, okay. So, this is what happens to this, to the phase plot, okay, of this particular factor. So, if you want to plot the phase plot, what will happen is the following, okay. So, let me plot the phase plot of this particular transfer function. So, this we are going to plot in degrees. So, let us say this is 0, minus 90, then minus 180, then we have omega n, 10 times omega n and 0.1 times omega n, okay. So, what is going to happen is the following. So, 0 to 1 minus 180 are the two bounds, and at omega equals omega n, you are going to have minus 90, right. So, what will happen to the phase plot is the following. So, as zeta starts to increase from 0, we are going to have the phase plot go something like this, and as zeta keeps on increasing, it becomes like this, okay. We are going to get a family of curves, right. So, depending on the value of zeta. So, this is for a lower zeta, okay. So, you are going to get a stronger inflection, okay. So, this is what happens as zeta increases, okay. So, that is just a family of curves, just to show you how the phase changes, okay, for this particular factor, okay, as zeta increases from 0, okay. So that is the phase of this particular second order transfer function, and if you consider the reciprocal of that, which is s squared plus 2 zeta omega n s plus omega n squared divided by omega n squared. So what will happen? You will just get the mirror image right above the 0 decibel line. So but I leave that to you as homework. Okay, so the seventh factor is essentially this, which is essentially the reciprocal of the factor that we just considered. So what I want you to do is do it as homework. Okay, so this will be a mirror image of this one. Okay, right. Okay, any questions here? Fine. So I am just going to leave you with one more question to think about, right? And then like we will continue and discuss it in the next class, right? And then we will do an example. Okay, in the next class we are going to do an example of the construction of the Bode diagram, but I am just going to leave you with a question, okay, to essentially think about. So we are done with this. Okay, so this next discussion is on minimum phase and non-minimum phase systems. Okay, so I told you that when we come to frequency response, I will revisit minimum phase and non-minimum phase systems, right? So do you remember what is a non-minimum phase system? Of course, we are assuming stable systems. When did we use the adjective non-minimum phase? Do you remember? When there was 0 in the right of plane, right? That was a non-minimum phase, right? When all the zeros are in the left of plane, it's a minimum phase, right? So I told you that, you know, like I will revisit and then like tell you the reason behind this terminology from the perspective of frequency response, right? I'm just going to leave you with a question from which you can figure out the answer, and then we'll anyway discuss the answer tomorrow, right? So let us say, consider two systems, okay, of course two stable systems, right, to begin with. All right, so two stable systems whose transfer functions are, okay, so G1 of s is going to be equal to 1 minus T of s divided by 1 plus T1 of s, okay. So T greater than 0, T1 greater than 0, okay, and G2 of s is going to be equal to 1 plus, let's say G1 of s was, I am sorry about it, let's say G1 of s is 1 plus and G2 of s, let's say we call it as 1 minus, okay, 1 minus T of s divided by 1 plus T1. This is not, sorry about that, this is T1s, right. So this is also going to be T1s, okay. So T greater than 0, T1 greater than 0. So immediately you see that both transfer functions have a pole at minus 1 by capital T1, which is in the left of plane, right. No issues regarding the stability of either systems, right. So what is the magnitude of the sinusoidal transfer function? So but before we calculate the magnitude, let's write G1 j omega, that's going to be equal to 1 plus j times T omega divided by 1 plus j T1 omega, right. I'm sure you agree, right. I'm just substituting s equals j omega, that's about it, okay. Similarly, G2 j omega is going to be 1 minus j times T omega divided by 1 plus j times T1, right. So what is the magnitude of G1 j omega? It's going to be square root of 1 plus T squared omega squared divided by square root of 1 plus T1 squared omega squared, right. So as I told you, you just need to take the as it stands, you know, like whatever factors you have, you take the algebraic the ratios of the individual factors themselves, right. So that's it, right, the magnitudes of the individual factors, right. So what is the magnitude of G2 j omega? Is going to be 1 square root of 1 plus t squared omega squared divided by square root of 1 plus t1 squared omega squared. So what can you say about the two magnitudes? Same, right, they are equal in magnitude, right, for all omega. So you give me any omega, you can see that the magnitude of G1 j omega and magnitude of G2 j omega are the same. Now let's look at phase of G1 j omega. Okay, what is the phase of G1 j omega? It is going to be tan inverse of t omega minus tan inverse of t1 omega, right. So then what is the phase of G2 j omega? It is going to be minus tan inverse of t omega minus tan inverse of t1, right. So what do you think happens to the phase of G1 j omega as omega tends to infinity? Tends to 0, right. What can you say about the phase of G2 j omega as omega tends to infinity? It tends to minus 180. So which has the minimum phase? G1, right. Yeah. See, G2 j omega phase tends to minus 180, G1 tends to 0, right. So I hope it's clear now why the system with the transfer function G1 is called minimum phase and why the system with the transfer function G2s is called non-minimum phase. So in essence what we are saying is that if you give me two systems whose transfer functions have the same magnitude characteristics, the minimum phase system will have the lower phase. Of course, the thing is that like we are only looking at the magnitude per se, right. So not the essentially the sign, right. So essentially it will have the minimal phase, okay, like of the two, okay. That's why it's called as a minimum phase system. The question I am going to leave you with is that how can we generalize it for any nth order system? Okay, let's say, you know, like what was our general transfer function? You remember? G of s was n of s by d of s, right? N of s was a polynomial of order m, d of s was a polynomial of order n, right? How can you generalize it for any nth order system? Okay, so that is a question I leave you with. Or if I give you the Bode plot of a transfer function, by looking at it, can you get the relative degree of the system? What I mean by the relative degree is what is called as n minus m. N minus m is the relative degree of the transfer function, and also figure out whether it's minimum phase or non-minimum phase. Okay, can we do that? Okay, so those are questions I'm going to leave you with. I'm going to come and discuss the answers tomorrow. Okay, so but please think about them. Okay, we'll discuss those answers tomorrow, and then we'll also do an example problem, right, in tomorrow's class for the Bode diagram. Okay, which would complete our discussion on Bode plots. Fine. Okay, so I'll stop here. I'll see you in the next class. Thank you.